Yeah, thank you. And yeah, we really got the speed dating slot. So thanks for trying to speed up, and hopefully, I mean, we can see if we have a bit of time and for discussion at the end. We could also reflect a little bit on both sessions together. I think that certainly there's a lot of similarities involved in it. If you can pull up the first one, the top one, please. So just basically 2 remarks to kick us off from Yuri and myself. Basically just, oops, here we go. So we want to basically broaden up even a little bit further and look at, let's say, heterodox approaches to scenarios or scenario thinking, or approaches that have been around to kind of reflect on how to present future climate risks that may or may not need scenarios or use very different frameworks for it. We have Ben Sanderson presenting, kicking us off in person. Then we have one presentation by Jeremy Fike virtually, who's online on Zoom, so we hope everything's going to work out well. And then we have him to be closing us off, and then we hope we have still some time of discussion also more broadly across all things. Yuri and I want to quickly show basically two slides, and this is interestingly picking up from a communication session that we just had earlier, where I had it over and where we ended up with a discussion about basically the storytelling for different audiences, and basically also a bigger concern about how a scenario is still not a prediction or projection, but actually a quantified narrative that we deal with in different ways. And what does this mean actually for the audience, and what kind of quantified narratives would stick with different people? So this is really our purpose. We want to explore options that go out of that space and have contributions and discussions around those, and just kind of to have one approach to get us all thinking that we wanted to kind of share a view that's a bit from a Horizon 2020 project called Provide, where we're working and where we try to explore whether or not it's actually possible not to start with a classical scenario that looks at different emission outcomes or concentration pathways, but rather start from the end and say, okay, what is actually a societal risk and an evolution of a societal risk I want to see, or I'm willing to consider, or I'm basically want to have information on, and what's basically going back into the emission space, what emission pathway would be aligned with me not having a certain risk. And these are things, you know, probably that could get us thinking. So how do we think about scenarios? What do we think end users are interested? And I think, Ben, you're in the perfect position to kick us off on that.
Cool. Thank you. Right, thanks everyone. So yeah, I'm going to be presenting some early work from the Provide project, which Carl and Yuri are heavily involved with. The project basically started with the illustration that Carl showed on the previous slide of what if we didn't take our starting point for scenarios as being an emissions pathway, but we started with a geophysical impact and then mapped forwards and backwards from that. And then we started the project and we realized that we needed to actually work out how to do this in practice. And so this is our first attempt at attempting to do so. Picking apart what this figure illustrates, on the left-hand side, we start with a set of geophysical thresholds. So these could be, in a simplistic way, these could be global mean temperature levels, or they could be specific geophysical thresholds which are relevant for a particular impact. And then given that condition, we want to map both forwards to the range of impacts which are compatible with those geophysical impacts, those geophysical thresholds, but also map backwards to see if we could describe the space of compatible emissions pathways which would result potentially in that outcome. So to think about why you might want to do this, let's think about a conceptual tidal barrage. And think about the status quo in terms of what we have at the moment. We have various different ad hoc selections from the scenario space. And then we can assess for each one of those scenarios what our relative likelihood is of exceeding our geophysical threshold of interest. But it's difficult given such a framework to say anything objective about whether we're either missing scenarios or comparing the similarity of scenarios which we're presented with. So the alternative framework which we're aiming for here is to describe a continuous space. And so this is a simplistic representation of what such a space might look like. But if we talked about a space defined by 2030 emissions and net zero date being the most simplistic breakdown of the future scenario definition we could come up with, then our desired risk tolerance for the dam we were thinking about building would then be associated with a region of that space. And so this is an alternative scenario framework which tells us what we should be fighting for, given an impact community looking at a specific threshold. So the project works in two directions. So we start with a densely sampled space of future emissions pathways. So in the CO2 space, this is defined by near-term emissions, by net zero date, and by the potential CDR floor in the future. And then we have other dimensions which represent other greenhouse gases. So this is by looking at correlations between CO2 emissions pathways and other emissions pathways from the scenario database. We can pick out, for example, methane emissions pathways, which are central estimates, high or low estimates, based on those trajectories. So if the forward model tells us can take each one of these four parameters, so 2030 emissions, net zero date, CDR floor, and the methane scaling, we then run that in the forward sense through its simple climate model, which has uncertain parameters representing the carbon cycle, equilibrium climate sensitivity, and transient climate response. And then out of that, we get an ensemble of global temperature pathways. And so then the question is, can we make this thing work in reverse? And so the way that we're doing this in practice is statistical. So when we take the outputs of the temperature output from this densely sampled scenario space, there's only really a few degrees of freedom in the shape of the global mean temperature pathway associated with which can describe the variance within the ensemble. And so we can, given a set of three parameters describing the degrees of freedom in the temperature pathway, we can then reconstruct the original temperature pathway associated with any given scenario. And so then we exploited machine learning model to take those three parameters, which define our temperature pathway, and then map back to this emission space. And so in the framework that we have, this works really quite well. So on the x-axis of these plots is for each one of our emissions metrics shows what the original value was in the ensemble. On the y-axis is the reconstructed value, taking the temperature outcome of that pathway and then going back to the original scenario. And so then we can think about what this would look like in practice given a specific goal. So if we have a temperature pathway, so if we consider a dense sampling of our temperature pathway space, and then we restrict ourselves to scenarios which are compatible with a stable 1.5 or 2 degree climates, we can then look at how what those shapes look like in our emissions definition space. So the green, orange, and blue distributions here correspond to different levels of climate mitigation expressed through the relative roles of the net zero date, the near-term emissions, and non-CO2 emissions. That's all I have. So thanks.
Brilliant. Thanks much, Ben. And also thanks for sticking to time. I think like the previous session, we would take all of them in a row and then have questions at the end. Yeah, so we don't have the video for Jeremy. So Jeremy, would you be able to speak to your slides and we just move them forward? Can you hear us?
Yeah, I can hear you. Can you hear me?
Yes, loud and clear. So we just put the slideshow and we would move it here on this computer, and you just kind of go to the next slide, please, and then you move forward. Is that okay?
Yeah, that sounds great. Awesome.
Okay,
thanks everybody for bearing with me remotely. I'm calling in from the west coast of North America, so it's early morning for me, and I've been up since midnight listening to a lot of great talks. So apologies if I'm stuttering or a little bit slow here. So I'd like to follow on these really great mini talks with one that I think bears a lot of similarity, particularly to the last one. Thanks, Ben, and also to Jennifer's. It's centered around this question: which scenario should I use? Which is a question that I and my colleagues in the Canadian climate science, but more importantly, climate services community, really trying to help real world decision makers use climate information. This question is one that is asked of us all the time with the expectation that we have a good answer for it. And of course, we don't. So this has motivated us to try and actually think about circumventing this question by using an arguably novel ensemble of emission and Earth system models to actually try and quantify emission uncertainty, really specifically for the purpose of on the ground, regional to local scale, but very consequential in orders of billions of dollars worth of climate risk assessments here in Canada alone. Go ahead, please. Yeah, so the problem in a nutshell is that I think you can say it's something like this: the future uncertainty budget is not closed with respect to a physical climate parameter, and we can see that schematically here on this box. So this is meant to represent the value of some climate parameter, let's say temperature, some metric of temperature at some XY location on the planet and some time in the future. Let's say that matters to some health authority who's worried about a heat wave or something, right? So some arbitrary climate parameter. We don't know exactly what this number is for a few important reasons. We can think about those as dimensions to this three-dimensional box. The first reason we don't know this number exactly is just internal variability uncertainty. This is aleatoric uncertainty. This is just the fact that the climate system physically is a noisy, technically chaotic system, and we can't pin that down to an exact number, especially as we go farther out past, the 2-week weather forecast window and out into climate projections space, end of the 21st century, for example. But we can quantify that uncertainty with tools like single model initial condition large ensemble, these fantastic computationally intensive databases coming from the climate science community. Another dimension, great, thanks for adding that up. We'll get to that in a second. The second dimension that we can think about in some sense quantitatively now is model uncertainty, epistemic model uncertainty. It's epistemic because it in some sense represents our imperfect knowledge of the physical climate system and our imperfect ability to represent this imperfect knowledge in climate and Earth system models, but we can quantify that uncertainty. That's the point here. We can do that with multi-model ensembles like CMIP. And we can combine these two ways of understanding uncertainty using this new really powerful tool that I love, multi-model large ensembles. And you can start to explore these two dimensions of future climate uncertainty, physical climate uncertainty, in a consistent statistical way. But that doesn't solve the problem because the final dimension remains unquantified. This is emission uncertainty. It's unquantified because almost unanimously now, explorations of future emissions are done through narrative storyline scenario approaches, right there. There's single storylines that bear no metadata describing which scenario is in some sense more or less likely to occur than another. Next slide, please. And so this is the challenge we hit, and we trying to think of a way around this. And our innovation here, we think, we would argue, and we welcome counter arguments against, is to combine a large ensemble, a very large ensemble of a simple energy emission model, CEPM, with 100,000 runs using Latin hypercube sampling. You'll recognize that from Jennifer's talk. To develop a series, a large ensemble of CO2 emission, carbon emission projections out to year 2100. what we can do then, because we have some control on the distributions of inputs to this model, is we have some confidence we can parse that ensemble out in percentile space and generate, in some sense, composite emission projections, and I use the word projection here somewhat consciously, across percentiles of this large single emission model space, and that's what you see on the bottom picture. Next, please. To move from there to physical climate projections, what we did was use a full CMIP grade Earth system model, CAN-ESM, the Canadian Earth system model, run 3 times for each of these percentile-based emission projections, and we run them 3 times to at least minimally swath out that internal variability uncertainty, the uncertainty related to natural climate variability noise. Next, please. That gives us, if you do the math here, 57 CMIP grade physical climate projections out to year 2100, but these do not follow scenarios. These follow emission projection time series that carry with them some sense of likelihood or probability with respect to each other, and thus with respect to the physical projections themselves. Next slide, please. And our final step was to, in the spirit of informing regional risk assessment, take a look at what this kind of information would do in terms of improving regional impact assessments, and we'll show that in the final slide. Next, please. We piloted this out for a particular impact that was near and dear to some of our hearts, which is the regional heat wave here in Western North America in 2021. Here's some graphic images of that. Lives lost, communities burnt. Go ahead, you can press forward to 2 times. Yeah, go ahead once more. Thanks, good. And so what you get when you bring in this information that carries with it some sense of likelihood of the underlying emission scenarios from the very beginning of the process are images like this. And it becomes very powerful then, because you can parse these projections, in this case of heat wave maximum length, a particular metric of heat wave changes over the 21st century, not just by time, which is the x-axis, but also by the emission scenario probability of exceedance, that's the y-axis, borrowing terminology that's familiar to people who use terms like 1 in 100. We're starting to use that kind of information to describe in a continuous sense the relative likelihood of one level of emissions and consequent impacts over another. That's powerful, we argue, because then you can start to make statements like this, which are of high value, I can attest, if we were to make them, or able to make them, to people making very consequential on the ground adaptation decisions. Based on current understanding and models, that's an important calibrated statement. Average maximum heat wave length for this region is extremely likely to exceed 4 days, but extremely unlikely to exceed 14 days by end of century. Now, what's most important here in this statement is actually what's entirely missing. This statement is not conditioned on any scenario, unlike almost every other talk I think you see here that's conditioned on one scenario or another and describes the situation resulting from that scenario. This case has emission uncertainty explicitly folded into the statement itself. Now, it's made with one climate model. You'd expand this out to multiple models, and so goes the story. But what's missing here is the most important thing of the statement, actually. In our is what we're arguing, anyways. Last slide, please. And so our outlook really is that this type of approach we know would be of real value to on the ground adaptation decision making. And so we would love to see this studied more for its strengths and weaknesses, and potentially thought about as some sort of parallel process to the scenario-based emissions scenario generation process for things like CMIP7. Next final animation. Coming from the climate science side of things, it excites us because this approach may allow epistemic, and I use epistemic consciously here, epistemic emission uncertainty to be quantified explicitly in the next generation of multi-model large ensembles, which are the tools, one of the main tools used to plan for and adapt to and become resilient to future climate, not at the global scale only, but also very importantly at the global and regional scale, the local and regional scales. That's all. Thanks a lot for having me remotely here.
Brilliant. Thank you so much, Jeremy. Our last speaker is Vin Thierry, again in person, and save your questions also for Jeremy. You'll stick around with us, hopefully. And I'm sure, like, please feel also kind of free to speak up if you want to have a contribution later in the discussion. So this is, please. So.
Thanks. Yeah, hi, good afternoon, everybody. So when I presented this talk recently, some of my colleagues came up to me before the talk and they asked me, Wim, are your children doing okay? And I had to tell them that my 3 children are doing just fine. And in fact, this talk is not about my children. Oh, no, it's not about my children, but it's about your children and children all over the world. Now, that said, let me nonetheless start by showing you a picture of my youngest son. This is Gaspar. And Gaspar was 0 years old in 2020. Now on the left, you see my mother, and my mother coincidentally was 60 years old in 2020. Those are some nice round numbers, nice to calculate with. So before we start this presentation, let me ask you a question. Think about someone that is really close to your heart, your children, grandchildren, parents, whoever, and try to think of their age in 2020. And if you do that, you can ask a question that looks like this. Will a newborn experience more extreme events than a 60-year-old? Who thinks that the answer to this question is yes? Please. Yeah, okay, I can confirm we have some experts in the room here. So the answer is yes, of course. But then comes the next question. And the next question is, sure, but how many more? And now this is something that we, as a climate and impact modeling community, have to acknowledge that this is something we hadn't really quantified until recently. Now, besides the fact that this is a question of huge societal relevance and also with a question with important legal implications, there's also scientific reason why this is important to do. And this is because it requires us to do our impact assessments in a different way than we are used to. This is how we typically quantify and analyze aspects of climate change. Here you see a diagram with time on the x-axis, and on the y-axis, we see an indicator of climate change. In this case, the land area annually exposed to an extreme heat wave. And we define heat waves here as a 1 in 100-year event under PI-controlled climate. Now, if you look at this metric, you see that it gradually evolves over time, with today about 15% of the land area annually exposed to an extreme heat wave. And as we go into the future, we have these policy relevant scenarios here, 1.5 compatible scenario. We have this indicator increasing to about 20%. Under a 2-degree compatible warming pathway, about 30% of the land area is annually exposed to an extreme heat wave. And under current pledges, so this is, let's say, the Glasgow era pledges 2.4 degrees of warming by the end of this century, we get more than 40% of the land area annually exposed to extreme heat waves. Now, the problem with this type of assessments is that this does not allow us to quantify what climate change means for a real person living in a real location. If you look at the year 2020 and you look at the 60-year-old, that generation was born in 1960 and will, on average, global average, live until somewhere in the 2030s. On average, a newborn in 2020 will on average live until beyond the end of this century. In other words, this generation will live to see the day when one of these potential future scenarios will become the reality. Now, in this study, we quantify the total number of extreme heat waves that a person will experience across their lifetime. If we do that, we get a graph that looks like this. Now, comparing 2 generations or birth cohorts compared to each other, the 1960 birth cohort will experience 4 extreme heat waves across their lifetime. And you see that this number is very much independent of the future warming trajectory. On the other hand, a newborn will experience 17 extreme heat waves across their lifetime, and this increases to 30 extreme heat waves under current pledges. Now, these absolute numbers that I just gave you are contingent on the heat wave definition. If we take a 1 in 10-year event instead of a 1 in 100-year event, those numbers will change. So what we do to overcome this issue is to look at relative differences between generations. So if you look at calculate the exposure multiplication factor relative to a reference generation, and you take the 1960 birth cohort as a reference generation, well, per definition, that generation experiences the same number of events. We can also do this for the newborns, and then we find that a newborn will face 4 times more extreme heat waves compared to the 1960 birth cohort under 1.5 degrees of warming. This increases to a 6-fold increase under 2 degrees warming, and under current climate pledges, grandchildren will face 7 times more extreme heat waves compared to their grandparents. Now, in this study, we did these calculations for every generation born between 1960 and 2020, and this is the graph with now on the x-axis age or birth year, and on the y-axis the exposure multiplication factor relative to this reference generation. So what I invite you to do now is to look at the age of your beloved one and to find out how many more extreme heat waves they will experience. Now, this work was done by combining 5 databases, 2 climate databases, ISIMIP, global scale impact projections, and GNT trajectories from the 1.5 degree report, and then 3 demographic databases on life expectancy, population density, and cohort size. Now, those were just 3 marker scenarios, but in the next step, we expanded this to consider the full range of potential warming pathways leading to a warming of present-day 1 degree levels all the way up to 3.5 degrees by the end of this century, repeating the analysis that I just showed you. And then you have this 2D graph with age on the x-axis and global warming level on the y-axis, and you can fill this 2D space with your exposure multiplication factors. And here's the result when you do that. Now, for every combination of birth year and global warming, 2100 global warming level, you can find a color which corresponds to the exposure multiplication factor, this time of a hypothetical generation living under PI controlled climate, so compared to living in a world without climate change. And if we just take one example, a newborn at 3.5 degrees of warming, the upper right point of this graph, this means that under 3.5 degrees of warming, a newborn will experience 44 times more extreme heat waves compared to a world without climate change. Now, thanks to the ISIMIP international impact modeling effort, we were able to do this assessment not only for heat waves, but for 6 extreme event categories in total, including wildfires, crop failures, droughts, river floods, heat waves, and tropical cyclones. So the graph for heat waves, you've seen that one already. We can now generate the same graph for all these other extreme event categories. And note that the color scale goes from 1 to 4 for all the events except for heat waves, where it goes from 1 to 30. And what you see on all of these graphs is that for generations of 50 years and older, there's not much difference in the vertical. But if you go towards younger generations, you see that the gradient starts to increase. So the younger you are and the higher the global warming level, the more lifetime extreme events the more extreme events you will face across your lifetime, and the more the global warming level matters for your life. If we just take one example, a 6-year-old under 3 degrees of warming, not by coincidence, the age of my oldest son in 2020, this generation will face twice as many wildfires, twice as many tropical cyclones, 3 times as many river floods, 4 times as many crop failures, 6 times as many droughts, and 36 times as many heat waves compared to a world without climate change. You might be thinking by now that we are all screwed when you look at these results. Well, I can assure you that this is not the case. And let me illustrate this by showing you this world map, because the actual analysis was done at the country scale. And if you look at this map, looking at showing the exposure multiplication factor on the current pledges for newborns compared to the 1960 birth cohort, we see these dark red colors everywhere, meaning that in every country of the world, newborns will face far more extreme heat waves compared to their grandparents in the current climate pledges. Now, if you draw the same map for 1.5 degree, you still see red colors everywhere, but you also see that the shades have become much lighter. This means that in every country of the world, there is a benefit of reducing global warming to 1.5 degrees instead of the 2.4 degrees of the current pledges in terms of the intergenerational burden. We calculated that we reduce the intergenerational burden by 40% for heat waves when we limit global warming to 1.5 degrees compared to current pledges, and that for the other categories, this gain ranges between 10 and 40%. So I can conclude to say that we must limit global warming to 1.5 degrees to safeguard the future of current young generations. Thank you.
Thank you, Wim. Thank you to all presenters, and thanks for sticking to time. So we have a little bit of time to still have some discussions. I think we had a wide range of heterodox approaches, so if you want to say so. So starting out from tell me your impact threshold, and we tell you how to get there, to well, I'm just want to know how bad or good it could become. So just give me a full range and don't tell me part of the story, to tell me your birth certificate and I tell you how bad it's going to be. So a lot of different ways of telling stories and narratives that are looking a bit outside of the classical scenario thinking. Thank you all. And I want to apologize. I wanted to say this in the beginning. We've had a very unfortunate gender balance in our session. This was not our desire and not by design. So we hope if this was ever a repetition of this session, we would be much more successful to also attract more presenters, more female presenters and more diversity in our session. With that, I want to open the floor to questions and at least hope that we will have a more balanced discussion. So I would encourage also some of the females in the audience to kick us off. Anyone? Yeah, so there's a question there in the back.
Hi, Jeremy. This is Castro from University of Waterloo. Do you hear me?
I can, yeah.
Yeah, thank you. That was an interesting topic, and thank you for raising this controversial topic on likelihood and probability. But I was wondering, all these ensembles are about the RCPs and different emissions. Yeah, you should, or about the SSPs. The problem still exists, as far as I think and I believe. Am I correct or not?
If I understand your question right, the approach we took doesn't use any of the RCPs or SSPs. It's really completely independent of those, and so it's not a matter of us choosing a particular scenario based on our results. If that is that where the kind of answer you were expecting to the question you posed?
No, actually, because I saw the paper by Schneider that you mentioned there, that was about the probability to the IPC scenarios, or now this current generation is SSP RCPs. I thought that the approach that you're presenting here are suggesting a way to assign those probabilities to those different RCP SSP scenarios.
That's one application. In fact, a colleague of mine, David Huard, has a poster in this workshop describing a paper in revision that does that. So it tries to use not just the results from the CEPM model that we use, but a series of other ones that look similar, to actually assign some numbers to the SSPs and RCPs. But that's not, we kind of decided not to even try and do that, and just looking at our own ensemble, assess the range across that without referring it back to the RCPs or SSPs themselves.
Yeah, thank you. That's great.
Thank you. Thank you very much. We have a question there in the back, please. And then Ben, I've seen you, so yeah.
Yeah, really interesting session. And thank you to all the speakers for these great talks. Jeremy, I also had a question for you so I understand how you did your probabilities for your own ensemble, but then if you were to move this to a multi-model environment, how would you establish the probabilities across scenarios, across different modeling environments? And I mean, I'm wondering if you would end up in a situation where you would have the sum of probabilities of all scenarios across the full ensemble would be more than one.
Thanks.
Yeah, great.
Could you give your
Oh yeah,
your
sorry,
name?
Jessica
So, yeah.
Jewell, Chalmers University.
Okay, cool. No, great question. And I don't think I have a particularly good answer to it. We've pushed this as far as thinking it through, and arguably not even thinking it through completely, for one Earth system model and one equivalent of an IAM and emissions model. But if you increase those numbers to n greater than one, either for the emissions model or the Earth system model, it gets very interesting, I think, statistically. Also a very big data problem, and I think it's an open question, honestly, how to proceed there. I suspect there's ways to do it, but don't quote me on that.
Great, thanks. Ben, yeah, please. And before you take the floor, just housekeeping announcement. We are approaching the top of the hour, and I'm acutely aware that there's a bus leaving, so some people might want to catch the earlier bus who don't participate in the the session. So unfortunately, Yuri also has to leave us. But for everyone else who's not up, we could maybe stick around for a few more minutes, and also maybe reflecting back to the previous session. Maybe also if you want to come and share perspectives on how these the presentations interrelate, I think we would very much all appreciate that.
Yeah, my question spans both sessions really. So it's about priors, and it applies to Chris's talk, and it applies to Jennifer's talk, and it applies to Jeremy's talk. In the we're like from different directions, we're coming at this point where we have to assign prior probabilities to some scenario space which we've identified. And Chris mentioned sort of like one way of dealing with that by looking at the historical performance, but most of the scenarios only really start to diverge in the future. You know, the strategies only become different in the near future. So so we have to, and for Jeremy's talk, we sort of this is the nice set of CO2 scenarios which span the plausibility space. But what we don't know from that is like what's the relative likelihood of something in the middle of that distribution and something on the edge. And for Jennifer's talk, we sort of if you start with the Latin hypercube approach, like the first thing that we need to identify is like what corners of that space are like mutually incompatible. So what assumptions about CDR? What about the carbon cycle? You know, where do we rule out parts of the space which we could never get to? So I feel like this is really promising work from lots of different directions and lots of parallel themes and nice ideas. But we need to get a handle on like how to objectively quantify our prior confidence in whether a scenario is representing a plausible future or not. And I don't know who's that to.
Yeah,
but Chris could take it.
Big question.
Yeah.
Looking online, Jennifer's nodding. Jennifer, you want to kick us off with a response?
I think it's a great question and a fair one, and there's not an easy answer. From the type of approach I'm doing, the biggest open question in my mind is what's the correlation between the input distributions, and especially when you get into the socioeconomic world, that's a big question mark, right? And we have some things where we have greater confidence that there's correlation based on maybe, you know, past relationships between, you know, population and GDP. And there are other things where we just don't know how things might be correlated. And so the sampling approach can, in fact, sample corners that might not be compatible. And so you still need to combine an approach like this with kind of expert judgment and ruling out corners of the space that might not be consistent or realistic, until we can figure out some methodological approaches to get beyond that. But I think the idea of a more exploratory modeling approach that is trying to get at all these different corners can get us a long way in exploring space that we haven't explored yet. With that caveat that we still have to layer that with our judgment of what's realistic. But yeah, fair question. I love to push further in the methods to get at it.
Great, Jeremy, do you want to? Or do you have or you don't have to? But just I didn't.
No. I mean, I think it's a great and super important question too, and we've been banging this topic around in our little group, working on our thing. And I mean, one thing we come back to is one way to be objective and think about how to evolve something forward is to be really transparent about the numbers you're using and the distributions. And they could be wrong. I mean, I don't discount the fact that inputs to our system are wrong or they're correlated or all sorts of issues, but we can state clearly what we're putting in and then evolve that and observe that evolution of those numbers forward with time. Some sort of Bayesian or epistemic uncertainty thinking applied to these things. So it's all at least it's very transparent, is one thing that comes to my mind in response to your question,
Ben. Thanks, Ben. Excellent question. So any Bayesian will know that the posterior depends very heavily on the prior. So you're absolutely right. Yes, so I mean, in terms of scenario weighting, there are other dimensions you can consider here. So, for example, feasibility of scenarios. So, Alina Bruchin at IIASA has done work on basically assessing how likely scenarios might be based on, for example, their rate of BECS deployment or sort of other sort of governance indicators, and these kind of constraints could possibly be applied to scenarios, because I think as a couple of people have given me feedback on, the sort of pure weighting based on similarity could quite easily leave you with infeasible scenarios that are quite wacky and not really similar to other scenarios just because they're different. So again, I think it's a very good point. You can be more intelligent about how you actually choose your prior scenarios and how you sort of sample the space of plausibility as such.
I think you can in some sense quantify your intuition, your expert judgment on the plausibility of some of the inputs to these systems, right? Like just the carbon tax growth over time or population changes. I mean, you can build a distribution, you can draw it or describe it in some numbers and make it reflect what you think. And it's not making stuff up. You're trying to pin down and show what your spread is that you think. And I think that's valuable. It quantifies intuition in a way. And I think that makes things quite transparent.
Yeah, and I was just about to say transparency is important, and basically, yeah, exactly, document your assumptions, and somebody else can come along and test them.
That's right. And when you draw a distribution, the tails are very explicitly the things that you think are kind of unlikely but maybe plausible, and then you can send those numerically through your systems, and you can get outcomes that somehow reflect your intuition about what's plausible and what's not. Yeah.
Okay, great. With that, I think we're gonna bring the session to a close. Thank you all for coming over here to the diaspora place. You online people can't see this, but we are a little bit outside the conference center, and we're very pleased to have such a full room. So thank you very much. Thank you also for the previous session for rushing through it. Much appreciated. I don't know if you want to say anything, just let Mike.
No, just thanks. I think this was really great, and I think there's a lot to research that we need to do in this field. So
thank you. So see you all over at the poster session.